Welcome to the concept of limiting reagent. Alright, so suppose you're working at a sandwich shop that only makes one type of sandwich, as follows. You get two slices of bread, 3 slices of meat, 1 slice of cheese, and 1 sandwich. Or that yields 1 sandwich. So suppose that you only have the following ingredients. You have 8 slices of bread, 9 slices of meat, 5 slices of cheese, and you want to know how many sandwiches can you make and what will be left over. So let's look. Let's first see how many sandwiches we can make with each ingredient. So with 8 slices of bread, we can make 4 sandwiches. With 9 slices of meat, we can make 3 sandwiches. And with 5 slices of cheese, we can make 5 sandwiches. So after our 3rd sandwich, we're going to run out of meat, so we can really only make 3 sandwiches. And then we're going to have some bread and cheese left over. So what will be left over? After 3 sandwiches, we will have used 3 sandwiches times 2 slices of bread per sandwich gives us 6 slices of bread used. 3 sandwiches times 3 slices of meat divided by 1 per sandwich gives us 9 slices of meat used. 3 sandwiches with 1 slice of cheese per sandwich gives us 3 slices of cheese used. So we started out with 8 slices of bread. We used up 6. We have 2 slices of bread left. We started out with 9 slices of meat. We used up 9. We have no slices of meat left. We started out with 5 slices of cheese. We used 3. We have 2 slices of cheese left. So in this example, the meat was our limiting reagent because that's the reactant that ran out first and thus limits the amounts of products that can form. It limits the number of sandwiches that we can make. Now, you could go ahead and make a grilled cheese sandwich, I suppose, with 2 slices of bread and a couple of slices of cheese. But that's not the same sort of sandwich that we were making before. Right? If you're only making one type of sandwich, you can't make any more sandwiches at this point because you've used up all the meat. So here's sort of a graphical representation of it. So again, in this example, the meat was our limiting reagent because we used up all of our meat and we have 2 slices of cheese left over, we have 2 slices of bread left over, we've made 3 sandwiches, but we've used up all of our meat, so we can't make any more sandwiches, assuming that this is how we're making our sandwiches. If we change our ratio, how many slices of meat we use, well then we can change how many sandwiches we can make. So this is something like a chemical reaction where we're using up some of our ingredients to form some product. So let's look at another example, a chemistry one. So here we have a molecule of nitrogen reacting with 3 molecules of hydrogen to give us 2 molecules of ammonia, NH3. So suppose we have this container over here. We've got this container, and we've got some big molecules, those are the N2 molecules, and we've got some little molecules, those are the hydrogen molecules, the H2 molecules. So let's group our reagents together with 1 nitrogen molecule and 3 hydrogen molecules that will react to form 2 ammonia molecules. So we group them together, and then we can go ahead and react them. In this case, it works out well. There's nothing that is unreacted. There's nothing that we haven't grouped here, and we've made 5 groups, so we've made 10 ammonia molecules. So because we have no unused reactants, this is a stoichiometric mixture, which means that this is a mixture that contains the relative amounts of reactants that match the numbers in the balanced equation. We have nothing that is unreacted here because we've got our stoichiometric mixture. We have our reactants in the right ratios. We don't have any extra of one reactant or the other. But now suppose we have a similar container without a stoichiometric mixture. So we have this container, and now we have a different ratio between hydrogen and nitrogen in that container. So now let's group together our molecules. So we have this group here, and that group there, and this other group here. And now you notice that now we have a couple of nitrogen molecules that are not being grouped because we've run out of hydrogen. So in this case, hydrogen is our limiting reagent, and we have 2 molecules of nitrogen left over. This is our excess reagent. So once we go ahead and react, we have no hydrogen left because we've reacted all of it, but we do have some of these, we have these 2 nitrogen molecules left over, and we still have our ammonia. In this case, we've made 6 ammonia molecules. So now let's look at an example with more than just a few molecules, more molecules that we can count. So suppose we react 25.0 kilograms of nitrogen with 5.00 kilograms of hydrogen to form ammonia. And what mass of ammonia will be formed? Well, first we need to convert mass of our reagents into moles of our reagents. So 25.0 kilograms, we're going to change that into grams with dimensional analysis, and then we're going to change from grams of nitrogen into moles of nitrogen, and we have 8.93 times 10 to the 2 moles of nitrogen. So we have 893 moles of nitrogen. And then we have 5.00 kilograms of hydrogen, change that into grams of hydrogen, and then change that into moles of hydrogen. And now we have 2.48 times 10 to the 3, so 2.48 thousand, so 2,480 moles of hydrogen. So now we need to figure out how many moles of ammonia we can produce from each reagent. So we have 8.93 times 10 to the 2 moles of nitrogen. Well, at 2 moles of nitrogen for every mole, 2 moles of ammonia for every 1 mole of nitrogen gas used, we get 1.79 times 10 to the 3 moles of ammonia that can be produced. And at 2.48 times 10 to the 3 moles of hydrogen, at 2 moles of ammonia per 3 moles of hydrogen used up, we get 1.65 times 10 to the 3 moles of ammonia. So we can produce more ammonia from the nitrogen than we can from the hydrogen. That means the hydrogen is going to run out first. Because we're going to run out of hydrogen first, the hydrogen is our limiting reagent. And now let's figure out the mass of ammonia we can actually produce using hydrogen as our limiting reagent. We know that we're going to produce 1.65 times 10 to the 3 moles of ammonia. We're assuming that all of it is reacting. So we have no hydrogen left over. We know that the molar mass of ammonia is 17.0 grams per mole, which means that we'll end up with 2.80 times 10 to the 4 grams of ammonia, which is 28.0 kilograms of ammonia. So now let's talk about percent yield and theoretical yield. So theoretical yield is the amount of a product that is formed when the limiting reagent is completely reacted. So all of it reacts away and we don't have any remaining at the end of the reaction. So this is the maximum amount of product that can be formed. We can't produce any more than that because we've used up all of one of our reactants. So we can't produce any more of our product. So often the actual yield is less than the theoretical yield because we don't normally use up 100% of our reactants. We use up a portion of it. So the percent yield is then the percentage of the theoretical yield that was actually produced. So the percent yield is the actual yield divided by the theoretical yield. These are usually measured in terms of masses and then multiplied by 100%. So if we had produced 25.0 kilograms of ammonia instead of the 28.0 kilograms that we had predicted, then the percent yield would be given by this equation. So 25.0 kilograms of ammonia that we actually got divided by the 28.0 kilograms that we expected to get times 100%, that gives us 89.3%. So if we had gotten 25 kilograms, we would have gotten 89.3% of the theoretical yield. So our percent yield would have been 89.3%. So that was the concept of limiting reagent.